Following up on our discussion about queue lengths, let's dive into the actual technologies we use to manage these messages. Message queues, specifically Kafka and RabbitMQ. At the heart of any message queue system are three core components: the producer, who sends the message, the queue, which holds it, and the consumer, who finally processes it. This structure is what allows for that asynchronous flow we just explored. Looking at this diagram, you can see how this architecture enables decoupling. In a decoupled system, the producer doesn't need to know who the consumer is, or even if they are online at that exact moment. They just drop the message in the queue and move on, which makes the whole system much more resilient. Now, not all message brokers are created equal. Take RabbitMQ, for example. It's fantastic when you need complex routing, like sending a specific message to several different services based on specialized rules, and it prioritizes reliable, guaranteed delivery. On the other hand, we have Kafka. Think of Kafka more like a high-speed, distributed log. It's optimized for massive throughput and streaming data. If you're processing millions of events or logs per second, Kafka is usually the industry's go-to choice. So, whether you need the surgical precision of RabbitMQ or the sheer volume capabilities of Kafka, both help us achieve a more flexible backend. Next, let's look at some practical use cases to see these in action. Now that we understand what message queues like Kafka and RabbitMQ are, let's look at how they solve real-world problems. These four scenarios represent the most common ways you'll see asynchronous messaging applied in modern backends. First, consider email or notification systems. When a user signs up, you don't want their browser to hang while your server waits for an external SMTP server to send a receipt. Instead, you push the send email task to a queue and immediately tell the user, "Success." A background worker handles the actual delivery separately. Next is video transcoding. Converting a 4K video into multiple formats is incredibly heavy on the CPU. By offloading this to a queue, your web server remains responsive to other users while dedicated worker nodes process the video files at their own pace. Traffic smoothing is another vital use case. Imagine a flash sale where thousands of orders hit your server at once. Instead of crashing your database with too many simultaneous writes, the queue acts as a buffer, allowing the database to process orders at a steady, sustainable rate. Finally, in data analytics, we use queues like Kafka to stream millions of user events like clicks or scrolls directly to a data warehouse. This decouples the live user experience from the complex analytical processing happening in the background. In all these cases, the common theme is decoupling, making sure one slow or heavy part of the system doesn't drag down the rest. Building on what we just covered regarding asynchronous communication, we need to address a critical question. How do we protect our backend from being overwhelmed when traffic spikes? That's where rate limiting and throttling come into play. Rate limiting is often applied per user. Think of it as a policy that says one user can only make 100 requests per minute. Throttling, on the other hand, is usually a system-wide safety valve that slows down processing when the server's CPU or memory is reaching a breaking point. The primary goal here is ensuring system stability. It's not just about stopping malicious DOS attacks, it's about fair usage. We don't want one noisy neighbor, one aggressive client to degrade the experience for every other user on the platform. To implement this, we often use specific algorithms. Let's look at this visualization of the token bucket. Imagine tokens being added to a bucket at a fixed rate. Each incoming request must grab a token to proceed. If the bucket is empty, the request is rejected or delayed. What's great about this specific approach is that it handles bursty traffic very well. It allows a client to use a burst of saved-up tokens for a quick sequence of actions, but prevents them from sustaining a high-speed flood indefinitely. Next, we'll dive into how to actually implement these strategies. Now that we've covered the theoretical algorithms, let's look at how we actually implement these throttling strategies within a real-world architecture. It's not just about the logic, but about where that logic lives. In most modern systems, your API gateway is the first line of defense. By centralizing rate limiting here, you protect all your downstream microservices at once, preventing them from being overwhelmed before the request even reaches them. However, implementation isn't strictly a server-side concern. Strategic placement also involves the client. If we can include logic in our mobile or web apps to proactively reduce request frequency, we save on network overhead and provide a much better user experience. When a limit is finally triggered, how should the system respond? We use the standard HTTP 429 status code. This clearly communicates to the client that they've sent too many requests, rather than a generic error that might lead to unnecessary troubleshooting. But don't just stop at the error code. Best practice is to include a retry after header. This tells the user's system exactly how long to wait, perhaps 30 seconds, or a specific timestamp before trying again. This prevents the thundering herd problem, where everyone retries at the exact same moment. By combining these centralized gates with clear client communication, we create a system that is both resilient and developer-friendly. Let's head to our final summary to wrap up everything we've learned today. We've covered a lot of ground today. To wrap things up, let's revisit the core pillars of backend communication patterns we've explored throughout this module. First, we looked at communication protocols. Remember that while REST is the gold standard for browser-based APIs due to its simplicity, gRPC is often the better choice for internal microservices where high-speed performance is the priority. Secondly, we discussed scalability through asynchronous patterns. Using message queues like Kafka or RabbitMQ allows us to decouple services, ensuring that a spike in one part of the system doesn't bring down the rest. System health is equally vital. As we mentioned on page 11, implementing rate-limiting and throttling strategies is a must to protect your infrastructure from being overwhelmed and to maintain security. Finally, the most important engineering lesson: always choose the pattern that fits the specific bottleneck you are solving. There is no one-size-fits-all, only the right tool for the job.